Institute of Engineering and Technology.
Hello students, after defining fundamental part of infinite sequence, which means we have defined some basic definitions of infinite sequences, like what do we mean by sequence itself, what do we mean by infinite sequence, what is convergence, divergence, what do we mean by bounded above bounded below sequence, and finally what do we mean by monotonic sequence. Now we are in this talk considering some fundamental theorems of infinite sequence. Our focus in this talk will be on some basic properties of sequences in form of theorems, like how to verify whether given sequence is convergent or not. For that we are going to discuss three theorems, which are sandwich theorem, continuous function theorem, and finally monotonic bounded sequence theorem. So let us start our first part, which is infinite sequences, and in that first of all I am considering sandwich theorem. So if I go through statement of sandwich theorem, it is something like this. If we have three sequence an, bn and cn of real numbers such that for all index values small n after some integer capital N, an is less than or equal to bn is less than or equal to cn for all small n greater than or equal to capital N, and at the same time limit of an and cn that is capital L. Now if I consider this whole situation graphically, then it simply means that we have three sequences an, bn, cn. bn is always remaining in between these two values an and cn. An is remaining always as a lower bound or the lower layer, cn is remaining always as the upper layer, and bn is somewhere in between these two. So that means we have three different layers, and these three layers can be compared with the real life example of sandwich. So if I consider cn, then it is the upper bread, you can say, of the sandwich. an is the lower bread of the sandwich, and bn is nothing but the filling of the sandwich. So this is how it is working after some values, which is capital N. And then I am imposing one more condition on it, that if my value of an and cn means lower layer and upper layer, they are moving towards the same value, then automatically you can see the filling which is remaining in between these two layers is also moving towards L. So that is nothing but our conclusion. If the upper and the lower bounds are moving towards certain value L, then obviously the value which is dominated by this 2 will also move towards capital L. Let us see some examples to understand this thing. If I take cos n upon n, it will tend to 0 as n tends to infinity. Now for this I am using a fundamental property of cos, that is cos always remain in between -1 to 1. So now if I take division of n throughout this, it will give me -1 by n cos n upon n less than or equal to 1 by n. And if I take graphical interpretation, then value of 1 upon n is given by point on the green graph which is remaining on the upper side. So it gives you the upper layer of this theorem. If I take -1 by n, it is given by that red graph which will be your lower layer of the structure. And if I consider cos n upon n, it will give you that filling which is remaining in between these two. And then if you look carefully, if I take n tends to infinity, 1 upon n as well as -1 upon n, both are giving us value 0. So obviously the value which is remaining in between these two for all n will also move towards 0, and this gives you conclusion of cos n upon n tends to 0 as n tends to infinity. Now let us consider another case. If I take 1 upon 2 raised to n, and if n is tending to infinity, it will obviously go to 0. For this, I am using the idea of 0 less than or equal to 1 upon 2 raised to n less than or equal to 1 upon n. This is true for all n. So here I am taking 1 upon n as upper bound, so it is actually green graph which is moving towards 0 as n is increasing. Lower bound itself is x-axis, so it is always equal to 0. Now if I take n tends to infinity, these two bounds are giving me value which is equal to 0. That means limit of 1 upon n is equal to 0. So the value which is remaining in between these two, which is 1 upon 2 raised to n, it is also moving towards 0. And this simply means that limit of 1 upon 2 raised to n is 0 as n tends to infinity. Now let us consider one more example. If I take fluctuating values minus 1 raised to n, 1 by n, then this is also tending to 0 as n tending to infinity. Here again I am taking the same case, minus 1 by n is less than or equal to minus 1 raised to n into 1 by n less than or equal to 1 by n. Now if I take graph of these two values 1 upon n by green graph, minus 1 upon n by blue graph, then you can see it is working as upper and lower bound. But now the value which is remaining inside, it gives me answer always on this graph. So it is not actually in between these two, but now in this example I am considering a case where it is exactly equal. So for the one value it is on 1 upon n, for the another value it is on minus 1 upon n. And then as the value of n will start increasing, it will move towards 0. This is whole idea about convergent sequence in form of sandwich theorem. Now let us consider another case, which is infinite sequences for continuous function. So if I consider statement of this theorem, then it is, if I take sequence an, which is a sequence of real numbers with its limit equal to capital L, then I can define a function f which is continuous at L and it is well defined at A, and if this is happening, then I can apply that function on the both sides of this equality, which simply means that if I have a convergent sequence towards L, I can define one more convergent sequence by applying a function which is continuous throughout on this sequence. Now how it will help you to check whether your sequence is convergent or not? Let us consider one example. Now if I ask you a question that check whether this root of n plus 1 upon n, it is tending to 1 or not as n tends to infinity, our simple observation would be, if I take denominators n separately with two values n and 1, then it will give me root of 1 plus 1 by n. And then as n tends to infinity, it will reduce into root 1, which is equal to 1. But now how to prove this using this continuous function theorem? So for that I need to have three values. The first value is function, second value is sequence n, and the third value is limit, which is capital L. And for that I am defining sequence a n as an plus 1 upon n. I am taking function f of x root x, and I am taking value of capital L as equal to 1. So now I can go for this theorem. Now we have all raw material for this theorem. We have function root x, we have sequence n plus 1 upon n, we have limiting value L equal to 1. Now this limiting value L equal to 1 is nothing but limit of an. So if I take n tends to infinity on n plus 1 upon n, it will result into 1. So now that means I can apply a continuous function on f of an equal to f of L. This is happening because my function root x, it is continuous at limiting value L equal to 1. If I take L equal to 1, my function is continuous remaining in this sequence. And so I can take this function f on both sides of this equality an and L. So if I apply function f on n plus 1 upon n and on 1, I will get result as root of n plus 1 upon n equal to root 1, and that is simply equal to 1. This means that limit of root of n plus 1 upon n is 1, and this we proved using continuous function theorem. Now let us move towards our last and the main part of this talk, which is bounded monotonic sequence. What is bounded monotonic sequence? See, if I consider sequence an which is both bounded as well as monotonic, then it is convergent. How we can use this thing? If I consider a sequence which is bounded and monotonic at this particular point, let me recall what do we mean by bounded sequence. By bounded sequence, we mean that our sequence is bounded above as well as it is bounded below also. We have seen this in our previous talk. If I consider monotonic sequence, we have two possibilities. It is non-increasing and it is non-decreasing. Now if I merge these two ideas in one statement, there is a clear possibility to discuss about convergence and divergence of the sequence. Now for that I have considered one situation over here. Suppose I take a sequence which is non-decreasing, that means after certain value of L, it will start slowly increasing or remaining at the same height. And then if I bound it above by capital L, then what will happen? After certain values, there will be infinitely many points remaining near that height capital L. And that means there is a cluster of points near height capital L, which simply means that if I take neighborhood L minus epsilon to L plus epsilon, there are infinitely many points in that band, and which gives me the condition for convergence. This is the scenario in which I am taking upper bound and I am taking non-decreasing sequence. So if this is happening, if your sequence is non-decreasing and there exists upper bound, for sure it is going to be a convergent sequence. Now in the reverse scenario, we can assume that your sequence is non-increasing, so it will start dropping down its value, and if it is bounded below, means it cannot move after a certain value in a decreasing order, then it will give you a clustering near to that lower bound, which will give you convergence. So this is idea about this theorem. We are increasing our sequence and then we are bounding it, so it will give you a clustering, so it is convergent. We are decreasing a sequence and then we are bounding it, so it will give you clustering around a point, and so it is convergent. So these three theorems are basically very helpful to understand nature of sequence in form of convergence or divergence. So in this talk, as we are discussing about sequence in form of its convergence and divergence, we have gone through three different theorems. Let me compile these three theorems. The first was sandwich theorem. In sandwich theorem, we are going for the upper and lower bound, and our sequence is remaining in between, and then we are verifying whether it is convergent or not. In second case, we discussed about continuous function theorem. In that, we have already a convergent sequence and then we are imposing a continuous function on that, and then it is helping us to construct one more continuous functions convergent sequence. And lastly, we have seen that what do we mean by monotonic bounded sequence theorem. In that, we have a sequence which is bounded below or bounded above, and it is non-increasing or non-decreasing respectively, to check whether our sequence is convergent or not. So I hope all of you understand this first part of our third chapter, which is infinite sequence. In upcoming lecture, we'll see what do we mean by infinite series, what do we mean by convergent of that infinite series and divergent of infinite series. We'll also go through some basic tests to check whether it is convergent or divergent. We'll also see some other parts like alternating series and their test. Thank you.
LJ Institute of Engineering and Technology.